the XBee Series 2 radio in API mode. So the focus of this video, of this module, is going to be API mode as opposed to the AT or transparent mode we talked about previously. An application programming interface, API, is a frame-based method for sending and receiving data to and from a radio's serial UART connection, Universal Asynchronous Receiver Transmitter connection. It's an alternative to the default transparent mode, and it allows a programmer to achieve several tasks. We can change parameters without entering the command mode. We can view received signal strength indicators, RSSI values, as well as the address of packet sources. And then we can also receive confirmation of packet delivery, which is great for improving reliability of our network overall. Now, API mode provides a more structured way to communicate data, where it's transmitted through the serial interface in organized packets, more structured packets, in a organized manner, in a definite order. Now, this enables developers to set up more advanced, more complex communication between devices without having to go through all the work of defining your own protocol for that purpose, a custom protocol. Now, by default, the XBee devices are set up to work in transparent mode, the AT mode, and that's what we call it the default mode. All data received through the serial input is brought up and queued up for transmission, and data received wirelessly is sent to the serial output exactly as it's received, with no additional information tacked on, no header or footer or checksum elements, something along those lines. Now, because of this setup, devices working in the transparent mode have a few problems. To read or write the configuration of a device in transparent mode, you first have to transmission the device into what's called command mode. If a device has the need to send messages to different devices throughout the network, then you have to update its configuration to establish this new destination. So each time you need to set the DL and DH values, destination low and destination high addresses. And the device, again, must enter the command mode in order to set up the destination. So that's a limitation. Furthermore, a device operating in the AT mode cannot identify the source of any messages that it brings in. And if a developer has a need to distinguish between data coming from different sources, then the sending devices must figure out a way to include extra information that identifies themselves. And again, that would sort of fall into the realm of a custom protocol that you would be setting up. Now, to minimize or reduce the limitations of this transparent mode, Digi has set up an alternative called the API mode, the Application Programming Interface mode. Now, this provides a more organized, essentially a better way to communicate information, where the data is communicated through a serial interface, and it's organized and set and divided into packets, and they're transmitted in a predefined order. This is more similar to like a TCP/IP, the way that information is transmitted through the internet or by your Wi-Fi router or something along those lines. Okay, and so this enables, like we said before, this allows us to do more complex things with our communication pathways. Now, the API mode provides a much better way to do several different things that are going to be useful to us. Now, because there are different frames for different purposes, such as configuration and communication, we can configure our device without entering command mode. Essentially, we can include the parameters within the packet and send that packet off, and it'll parse everything out and use the information appropriately. Now, since the data destination is included as part of the API frame structure, we can use the API mode to transmit messages to multiple devices very easily. We can include in the individual packets in the appropriate frame the destination. We don't have to enter the command mode. And so these frames, the API frame includes the source of the message automatically. So it's easy to identify where the data is coming from, and there's no need to set up something on the sending end to tack on to that message something about the source of it. Now, there's a lot of pros for the API mode. There's some cons as well. You'll see there's more overhead involved. It's a little bit more difficult to work with, but I think the trade-off is a good one because it provides such a higher level of functionality. So some pros, right? We've talked about a lot of these just a second ago. You can configure the XBee devices remotely. You can manage more effectively the wireless transmission between multiple destinations, between your radio and multiple destinations. It's easy to identify the source of packets. It's easier to determine whether your packet has successfully been transmitted and received. You can receive signal strength indicators. You can perform more advanced tasks. So essentially, you can diagnose your network. You can look for problems. And it just provides a whole additional level of advanced functionality, which we're going to find useful. All right, so now let's talk a little bit about important parameters. I said in one of the other modules that we were going to come back to this and talk about some of the more important parameters, which we saw previously in the X-CTU software. So let's talk about those now. Okay, CH is the abbreviation for channel. This is the channel over which the data is being transmitted. AP is the abbreviation for the mode or the API mode. Okay, so if you set AP equal to 0, that indicates that you are working in the AT/transparent mode, again, like we did in one of the previous videos. And in that case, the destination of your packets or your transmissions will be solely decided by your destination address, DL and DH. Okay. Then you have two different flavors of your API mode. If you set AP equal to 1 or to 2, both will put you into API mode. The difference will be the firmware version that you use. We'll come back to that a little bit later on, but it's just important to understand that AP equals 0 means transparent, API equals 1 or 2, that means API mode. Okay, next, these are some that we've already touched upon, but I'll just quickly review them. We have SL and SH. Those are the abbreviations for the low and the high parts of the serial number of the radio. This is a 64-bit address, so either one of the two are 32 bits each. And they identify the radio with a serial number. Then you have MY, which is the abbreviation for the 16-bit address of the radio, which is different from the serial number. And so this parameter may be used in place of the SL low end. Well, actually, both of them. So it can be used in place of the serial number for 16-bit addressing schemes, which for most purposes will be an easier way of addressing the radios, especially if you consider you don't have millions of devices that require some sort of 64-bit addressing scheme. So we'll be relying heavily on MY, the 16-bit address. We've already talked about DH and DL. Those are the abbreviations for the destination high and destination low address. Again, this is 64 bits. Each individual piece is 32 bits. Okay, so let's talk a little bit about what those destinations mean within the API mode, because now we're not necessarily going to be setting a direct path between one radio and the other. So why do we need a destination address period? There's several different options here. One is that we use a 16-bit addressing unicast. So if our DH, high destination address, is equal to 0, and our DL is less than FFFF in hex, meaning that it falls within that 32-bit range, then the data transmitted will be received by any radio for which MY, the 16-bit address, equals DL, the low part of the serial number. DH, SL, and SH are not considered. So this is simply just saying we're going to transmit to anybody whose 16-bit address fits our value of DL. That's the first mode. Second is going to be a 64-bit addressing unicast. And for that one, we are going to be considering both DH and DL. And so data transmitted will be received only by the radio for which the appropriate DH and DL values are specified. So it's a lot like how it works essentially in the AT or the transparent mode, where we're defining a specific address and transmitting. Then we have the X-bit broadcast. And so for that, we set DH equal to 0 or null, and we set DL equal to its maximum value, FFFF, again in hex. And that means that data is transmitted and received by any and all radios in the broadcast area. And so for many applications, especially those with larger networks, that's going to be preferable because we're not looking to hide information from various radios. We want to throw it all out there, and then we'll let the radios decide, and we'll develop code that will do that. Let the radios decide what information they use and what information they relay back to the coordinator and how that's processed.
Next, we are going to take a look at a basic 16-bit addressing example provided below. So we have two radios, radio A and radio B. They're both going to be working in API mode. They have two addresses, 5000 and 5001. And for radio B, we've assigned the destination low to the address of the first radio A. Now, to compose a data packet as required by our API mode, the assemble packet option is used within the terminal tab of the X-CTU test and configuration software, and this is obviously something we've spent a decent amount of time talking about. We're going to select the hex option and enter the following hex formatted data for transmission by radio A. And the post looks like this right here. I'm underlining it. Okay. So now what I want to do is break this down so we can understand the individual pieces of that packet, of that message. Okay, first, what we have is the start delimiter for all packets, which is 7E, and that essentially lets the hardware or the software know that a new packet is beginning. Next, we have the length of the packet in bytes. In this case, the length of the packet is 10 bytes, hence 000A. Hopefully you're all familiar with counting in hex, right? We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, all the way till F. And that corresponds to, these are all the same. So 0, 1, ... all the way till 9, 10, 11. So A corresponds to 10, therefore 000A corresponds to a 10-byte message. Next, mode. 01, we are in API mode. Next, API frame ID, 1. So if it requires multiple messages to communicate an entire idea or whatever message we're trying to convey, so multiple packets to convey this message, then we'll assign them different IDs. Next, the destination address. So because this is being supplied to radio A, it makes sense that we are going to define its destination low as 5001 because that is the 16-bit address of our destination radio. Okay. Next, we have an option byte. We're not going to talk about that right here. Perhaps we'll get to it later. Then we have the 10-byte packet to be transmitted. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the line is drawn right there. 48, 65, 6C, 6C, 6F. So when we talk about this length here, it's not referring to the entire, it's not referring to the entire packet. It is merely referring to the load or the informational part of the packet that we are transmitting without the overhead and the headers and all that type of stuff. So this piece right here is 10 bytes. Next, we have a checksum at the end, B8, and that brings us to the end. All right, so quick review. Again, what we have is start delimiter, length of message, API mode, frame ID, destination, unused, or at least for our purposes, we're not going to discuss it, message to be conveyed, and then checksum. And that demonstrates how to build a packet that's appropriate for our API mode.
So that concludes our introduction to using the Series 2 radio in API mode. Next, we're going to move on to some examples and dive deeper into this topic.